this endpoint saturation's effect on the relationship of KRG to the ratio KRG, KRO. And I had made a comment which now in hindsight, after doing this exercise, Marcus did, and looking at it the last couple of days, was that people talking about how important SOC or SOR was being because of this effect that had on this relationship. It's not right. Okay, so the industry's insistence earlier and still to this day that this is important did not come, I think, from parametric changes in simulation models, because I was going to show you basically what happens if you have a relative probability, Corey type relative probability model. You generate this relationship, for example, with an SOR equals to 0.2, and then if you change this from 0 to 0.4, I was suggesting that would give a big impact on this function. So I'm going to show you what happens when you do that, which is what Marcus showed me earlier in the week, and I wanted to share that with you. So in this, you'll be getting this in the class. This is an Excel sheet that duplicates the method in sensor simulator called KR Analytical, where you can just give the Corey parameters. You can just go in and put the Corey parameters here, which are in red. So the contact water saturation, residual oil saturation to water, which is of no interest here. Residual oil saturation to gas, which is the one we're talking about. Critical gas saturation is also in our gas oil curves. The relative permeability of gas at contact water saturation, that's relevant, not necessarily equal to 1, but, and then we've got the exponents, NW, NOW are not relevant to what we're talking about, NG and NOG are. So the default case that I'm using is 20% contact water, 20% residual gas, residual oil to gas, critical gas at 0.1, and exponents of 3. All right? And with that, we get the base KRG, KRO. Okay? And that's given as a big, thick black line. And so these base case numbers, these are fixed. Now I can go in and change, and this you'll be able to do yourself, the endpoint saturations or any of the exponents, whatever you like. And then that line will, for the sensitivity, will give you, in fact, I'm going to just change that, the name of that to sensitivity. Okay. Like that. And that blue curve, now they're identical because the parameters are all the same. But if I change this residual oil to gas to 0, okay, and then look at the same curve, what you see is that there's hardly, even though it's a thick line, there's hardly line thickness change in this relationship. Okay? If we go to 0.4, which would be, of course, a big change, but that would be a big SOR. See a little more effect drawing this thing down. Now, the parameters I've selected give us the base case has a 0.1 KRG, KRO at the crossing. So that's a realistic type. And you see it's moving it down just to about 0.09 from 1. So it's not much change at all in this curve from going from 0 to 0.4. It's just not a big effect. So what I said was not right. That was not the only thing I said during the week that was not right, but it's the only one I'm admitting to openly. The other ones you have to figure out yourself. Okay? They're not said intentionally, but it's just that, you know. So if we go back and put this to point 2, that's our default, so these should now be identical again. Okay? Then we can try, what I thought we'd do is try, so SOR, little, very little effect. Okay? So that's our first conclusion. So now we're going to look at SWC, which is the most common thing we use for normalization, because our rock water, connate water saturations, they might vary from, from 0.05 to as much as 0.5. Now our default here, our base case, is 0.2. So let's look at the range of SWC going from 0.05 to 0.5 and see how that changes. So we go to SWC, we go to 0.05. Does anybody want to bet whether the KRG gets better or worse? Anybody not bet or guess? No? So
shouldn't change too dramatically.
Shouldn't change too dramatically, but do you think it'll get better or worse?
If we decrease, maybe a bit better, no?
Okay. Huh?
If you will get more pore space available to gas, then there will be slight improvement.
You think it'll be better? Okay. So I'm just going to tell you how I would think through it. Just, if I was going to make a bet, I wouldn't bet very much money. I'm not sure. But the way I'm looking at it is this: is that you probably need a certain amount of you need a certain amount of oil mobility. This KRO and KRG kind of to get, and so, but you don't have the water filling the pore. So I'm thinking you may have to have more oil, but the total liquid may be less. So if the total liquid is less, then the total gas saturation is more, and then you have a higher KRG, I think. So yeah, it's not very, so sensitivity is a little better. Let's go the other direction and go up as far as to 0.4. Okay. And then you see that with the 0.4, it actually gets better. Is that what it's saying here? Maybe I changed the numbers wrong. Okay.
0.4, it gets worse. Yeah. The blue line.
Oh, it's going less. Okay. It's Friday. It's in the morning, so it's going to be a long day. Yeah. So it's getting worse, but not a lot worse. Okay.
You see that it's good that you didn't bet anything on it.
Yeah.
Because even after seeing the result.
I have to tell you a true story. But you're going to laugh. Yesterday I was taking care of the grandkids. That's why I had to leave right at 4. So my youngest boy here in Trondheim, he's 3. He's 4, and the sister's 6. And he likes to eat. He likes sweets and everything. And I made him watermelon. I cut watermelon up for him. But his parents haven't been able to get him to eat watermelon yet. So he comes over and says, taste this watermelon. It's sugar. It's like sugar and water. But everybody says it's healthy. So this is the kind of thing you want to eat a lot of. Okay. He didn't believe me. It was pink, red. No. So, and I said, look, I'll pay you $100 if you just try it. I'm saying this in Norwegian. Of course, he doesn't know what $100 is either. But I said, but with that you can buy tools and equipment, because he loves saw. He wants a saw, and also he's 4 years old. So he walks away, says, no way. Okay. And about 30 minutes later, he walks back over to me, says, I want to try the watermelon. So I give him a little piece, puts it in his mouth, says, oh, that's good. He says, and you know what he says next? He says, what's $1? He said, "What's $1?" So I said, "Well, you now have 100 of them." So so I lost the bet yesterday. You know.
No, really.
It's a true story. I can vouch for it.
Yeah. So it's
What's the
crazy.
dollar?
Yeah. Anyway, no, I would have lost money. So anyway, you see that the water saturation endpoint is not changing things a lot for a large range of now 0.5. It's let's see, 0.5. That's kind of an extreme, and so now some of the laboratory experiments that we actually did to try to verify this, we went from like 0.2 to 0. Okay. And we didn't see in the laboratory, of course, the laboratory experiments are the uncertainty is bigger than the line thickness here, but we didn't see really much effect at all with and without water. Okay. So that, and then the last parameter is critical gas. So if we go to 0, which is kind of the lower limit, obviously, that's got a much bigger effect. Now the range of critical gas is about 0 to 0.2. That's the full range that you would expect anywhere. So you basically see that it's got a let's say a measurable effect, but none of these are moving far away from the base case. So what I would say is that the endpoint, so this has more effect, but still, I would not say large. And for the SGC, from 0 to 0.2, that's kind of the limit where 0.1 was it has some effect. But in none of these cases do we really deviate far from this crossing point of 0.1. Okay? Not really for any of these cases, according to 20% gas. So that was I just wanted to share this with you. And basically this means that there's some other bad reason that people are preoccupied with the critical oil saturation. Basically, you shouldn't be, in the long list of life's things to worry about, that's off the chart. It's not even on the list. It's not even on page 100. So, and certainly for condensate blockage, it's not an issue, regardless of the impact of that. So anyway, this is a sheet that I'll give you guys. You can do your own assessment. Now, if you do change exponents, I thought I would look at that. Just if you bring this back to, these are all the default values. If you start seeing the exponents of the gas like 2 and 4, like we had a really bad oil curve, and this doesn't change it much. If you go to 4 and 2, I think it's quite a bit more. Yeah. Getting much better. So you can do this kind of assessment if you want to, but bottom line, let's see, if you go to pore size distribution, it's something like this. It's I think if you use the core equation, pore size distribution, I think the one exponent to gas is higher than the exponent to oil, if I remember right. But what most people think is that they should be the same values, but they normally shouldn't, according to the Corey bundle of capillary method. So that's, I'm not sure what's changed here. They should have been.
This is the SWC.
SWC, I haven't gotten back to. Oh, that should be. Okay. All right. Anyway, I'll leave that.
What if you change the residual saturation and the exponent at the same time? Because normally this is what happens.
Residual to like 0.1 of oil? An exponent
Yeah,
of
then
which
you-
one?
And then you reduce the exponent also, makes it more straight.
Which one?
Of gas, let's say, or oil, both.
That?
Yeah.
That's a big effect. Now, whether it was the endpoint saturation, we have to check that first. Let's go back to point 2. Okay, this is only the exponent, so that's the biggest effect, going to 2. And by the way, this little spreadsheet here, if you want to know the straight line, now this is not exactly straight line because it's the endpoints are still non-zero, but this is this upper limit that we were talking about. If you really want to do it right, you have to take basically,
Why would it not be straight line when the exponent is 1?
well, it's straight line, but the endpoint should also go to 0 on oil and gas. Not that one. That's the gas. These two should go to 0 as well. So that's really the straight line. With
So that means that if we do the EOR and we inject surfactant, change the endpoints, and straighten the rail curves, then this model wouldn't be applicable. Is that correct?
well, no, the capillary number model is actually moving you from the black to the blue curve. That's what the capillary number is doing. And if you lower the IFT, like you're saying, to very low value, then you'll move from the black curve to the blue curve, yeah, or high velocity, or both.
Yeah, but then there was also some effect of endpoints, or wasn't it? I missed this part. I mean, if you just change now back to
Yeah, you probably don't see the effect of endpoints so much in this figure because we're looking at a fairly narrow part, this KGKO. You'd need to look at the saturation figure more than I didn't do it for both the base but within this range, the endpoint saturation is probably not having too big an effect on the blue curve here, the straight line curve.
okay.
Anyway, this is a I think a sheet that is okay to have to try to get this back to the original. Point two. Point 1. There we go. Yeah. So again, this curve or this Excel sheet was more to do this study, but you can use it for just getting a handle on. Like I said, if you know nothing, make sure that whatever curve you use as a base case has a crossing point 0.1 or less. 0.1 is optimistic. It's what we see for Berea type things. And 0.05 and lower is what we see for lower perm. So if you want to look at a range from kind of optimistic to pessimistic curves, you can come up with a couple of tables from this Excel sheet.